Hello everyone, welcome to the final presentation of the autofocusing and color identifying lenses for mild visual impairments, also known as P.A.U.L. Our team consists of Julie Gallagher studying electrical engineering, Renato Morales Jr. studying photonic science and engineering, Midhat Satonov studying photonic science and engineering, and Kayla Stanley studying computer engineering.
The idea for P.A.U.L is to create a set of lenses that would assist visually impaired individuals with their various visual disabilities. And some key features that we want to include in order to help with that would be autofocusing, color identification for colorblind individuals, and an auditory response to assist with those features. So our background for pursuing this project was that we know that there are billions of individuals around the globe who have some form of near or far-sightedness. And there's also a pretty substantial portion of people that have some sort of color blindness. And while there are current assistant apps that do help them, all of those rely on volunteers. And so we wanted to create a device that would be able to provide those individuals with more freedom and improve their quality of life. Here we have our requirements and specifications, and there are a few that we have chosen to specifically focus on. These are the time to focus, which we are trying to reduce below a minute, and then also the color accuracy, which we hope properly detects the correct color that is being shown in front of the device more than 80% of the time, and also a focusing power that provides between negative 1.5 to positive 2.5 diopters. So here, we want to show a basic idea of how exactly the system works. This is a schematic of our autofocusing system. It relies on an infrared sensor that sits on top of the frame of the goggles in order to determine the distance between the frame and the object that the user is staring at. Upon activation, it transmits this data to the PCB, which then moves the motor and rail system that then move the lenses and determine the optical power of the system. And to ensure that it's now in proper focus, we have a CMOS camera off to the side of the frames that also has its lens system moved and determines whether or not the resulting image is blurry. Here's the schematic for our color identification system. So, using that same CMOS from earlier, we pair it with a colorimeter in order to determine the color of the object that is in front of the user, and it measures the light rays coming into it. Then that information is transferred to the PCB, which interprets the color and transmits this information to the user, doing so by sending a Bluetooth signal to an external speaker. And here we have a schematic diagram of our optical system. It includes the various lens systems, the rails, the motors that guide them, our ultrasonic sensor, our Raspberry Pi camera, and also our colorimeter.
For our goal specifications, we are once again focusing mainly on the basic and advanced goals. For our basic goals, we want to achieve accurate distance correction based off the autofocusing algorithm and the calculations acquired from the time of flight. We also want it to be able to identify correctly when the lenses are in focus, and we want it to be able to identify at least 3 colors and have a fully functioning auditory speaker system. Moving towards more specific specifications, we want to achieve at least a negative 2.5 diopter to positive 1.5 diopter optical power adjustment within 5 seconds and have color identification accuracy above 80%.
If we had had more time, we would have implemented a more compact system and added more convenient features such as more identifiable colors, adding a text-to-speech feature, and object identification.
We have our objectives split into 3 categories. Our main focus is what is listed in the basic and advanced goals. In the basic category, we are working on the foundational features of our autofocusing and color detection glasses. This includes an accurately working infrared sensor and motor rail system that can adjust the focus at different distances, as well as a matching algorithm to perform edge detection. It also includes a color detection software and an accuracy check with photodiodes and an auditory response. Our advanced goals are focused mainly on improving accuracy and efficiency within the system, and the stretch goals will be more advanced features that will be added if we have the time.
Hardware design. On these few slides, I'm gonna explain more about our hardware block diagram and our prototype. Hardware block diagram. Our hardware design, as illustrated in the diagram, features a main PCB that integrates the ESP32 and two voltage regulators circuits. The ESP32 is responsible for programming the majority of our peripherals, including the ultrasonic sensor, TCS32000, color detector, and 3 servo motors. Additionally, a secondary MCU, the Raspberry Pi 4, is dedicated to programming the CMOS camera. The design includes two motors to adjust the lens's position in front of the user, and a third motor to control the lens in front of the CMOS camera. User input is provided through push-down buttons, while output is delivered to the user via audio. All components are housed within a cap design prototype, which is designed to enclose the peripherals, PCB, and Raspberry Pi.
We 3D modeled our system as seen to the right here. The initial design involved the use of a visor to provide support for the components while maintaining optical alignment. Moving forward, we chose to utilize a flat-brimmed ball cap. The components are placed around the hat to evenly distribute the weight of the components. The primary lenses are aligned with the user's eyes, and the secondary lenses are aligned with the CMOS sensor. The ultrasonic sensor, as well as the color identification system, are attached to the brim of the hat so as not to impede the user's vision. Let's begin with the comparison and selection of hardware. For our autofocusing system, we'll require a time-of-flight sensor that will give us a starting value for the focusing distance. We compared three different types of sensors: laser diode-based sensors, LED-based sensors, and ultrasonic sensors. We considered several options across these types of sensors. While the laser diode options certainly had the greatest measurement range and accuracy, they were significantly more expensive than all other options. Moving on to the LED options, these were much more affordable but only functional at shorter ranges. Lastly, the ultrasonic options were definitely the most affordable and capable of measuring up to approximately 4.5 meters, which is more than enough to acquire a starting distance. Luckily, a member of our group had already purchased an ultrasonic sensor for a previous project, so we decided to go with the HC-SR04. For our autofocusing system, we will have a variable optical power that ranges from negative 1.5 diopters up to 2.5 diopters. To accomplish the variable focal length and thus the variable optical power, we'll be putting the lens maker's equation into practice. Through the use of at least two lenses, we can estimate the effective focal length by imagining the system as a single very thick lens with a variable thickness. Taking into consideration various lens shapes and their interactions with light, we determined that we'll require one converging lens and one diverging lens. By using a positive lens with a negative lens, we can maintain an image with a positive orientation while minimizing the distance between the lenses. While looking at our lens options, we considered the availability provided by United Scientific, ISCO, and Edmund Optics. We need lenses with diameters that range from 25 to 50 millimeters and focal lengths that range from 50 to 200 millimeters. Ultimately, we chose to move forward with ISCO lenses because they had all these options available at the lowest prices.
For our design, 3 motors are required. We consider various factors with particular focus on the motor's torque, as it needed to provide sufficient force for the linear motion of the lenses. We also accounted for size and weight of the motors, as the placement within the design was crucial and to ensure comfort to the user during extended hours. Motor comparison table. We initially explored stepper motors, especially the NEMA 17 and NEMA 8 models, which offer similar capabilities between them except for size and other parameters. The NEMA 8 is of smaller dimensions, however, the size and weight were still larger than what we desired. We also researched servo motors, first being the MG90S, as it offers smaller dimensions. We also considered the MG996R servo motor, which was lighter than the NEMAs, but it required modifications to turn the motor into a continuous rotation motor. Therefore, we picked the MG90S. Power supply comparison. On the next few slides, I'm going to talk about our power distribution table, our regulators, a comparison table of the different types of batteries, and what battery we have selected. Power distribution table. On this table, we're outlining all our electronic components and figuring out their voltage and current requirements. This information will be used to pick our regulators and our battery selection. Battery comparison table. To select the most suitable battery for our design, we compare for different types as shown in the table. After considering factors such as lifespan, safety, and voltage stability, we opted for a lithium-ion battery due to its longer cycle life and reliable performance. Battery selection. After deciding on a lithium-ion battery, we compared three different battery packs, but selected the first option based on price and current capabilities. Regulators. For a 3.3-volt regulator, we compared different LDO regulators, but picked the AMS1117 as it provided enough power for a 3.3-volt peripherals. It is also a simple design. For our 5-volt power regulator, we compared a couple different types of regulator, but decided on a step-down regulator considering our battery is of 12 volts output. We picked the LM2596 as it met our requirements and had a simple design.
In terms of selecting the proper logic device for a project, I was focused mainly on processing power, camera interface, number of I/O ports, memory size, and power consumption. For a more broad category comparison, I first looked into MCUs versus FPGAs. The biggest difference and deciding factor between the two is the ease of coding and development time, and the ability to add on extra peripherals. FPGAs do not utilize high-level programming languages and are not as modifiable as MCUs. While our project did require fairly large processing power, it wasn't necessary to use an FPGA. And moving on, I looked at quite a few MCUs, most of them being more budget-friendly and compact, and in the end, the biggest deciding factor is processing power. Just about all the MCUs researched were crossed off due to them not being able to handle image processing or not having some sort of camera interface. The only boards we're really left with were the Raspberry Pi 4 and 5, and we decided to go with a 4 to fit more within the budget.
Comparison of our main MCU. So for our main MCU, we picked the ESP32 Room 32D as it had all the requirements we needed. It was of a good price and not much power consumption. We also looked into the STM32, but we didn't really need too many pins, and the complexity of the design was higher than the ESP32, which led us to pick the ESP32.
One half of the color detection system required processing live feed from a video camera, and we also needed to use that same video camera in order to determine the focusing power required for our primary lens system, and so we had to figure out what kind of camera we needed. The first consideration that we needed to take into account was whether or not we wanted to go with a CMOS or a CCD camera. So CMOS, or complementary metal oxide semiconductors, have smaller power consumption, faster processing, are more greatly miniaturized, and have a lower signal-to-noise ratio. Whereas CCDs are in general more expensive, but boast higher image quality. For the actual camera considerations, we wanted our camera to be as similar to the human eye as possible. And that included having a high resolution, having an image format that is similar to the size of images that the eye sees, a field of view that is as similar to the human eye as possible, and also a comparatively similar focal length. Thus, after we considered all of these factors, we first decided that we were going to pursue a CMOS camera. And that specifically is just going to be because of price considerations, miniaturization, and also because they're generally more common these days. And after considering several options, we actually decided to go with the cheapest and in some ways worst option, the camera module version 2 for our Raspberry Pi. And the reason why we decided to go with that is specifically because it does not have any built-in autofocus features that we would have to edit out in our programming. Since we want to be the ones deciding what the autofocus is going to be, that is going to be the most important factor in our decision. Also, it does have a very similar field of view to the human eye. Now, our color detection system is twofold, and it requires a color meter on top of the CMOS camera. There were essentially two choices that we could go with for our color meter, the TCS 3200 and then the TCS 34725FN. Now, the difference between these two is Very minimal. But in general, the TCS 3200 is less compact but has higher accuracy, whereas the other option has a shorter range and a smaller light collection area. Because our desired parameters include as high of color accuracy detection as possible, we decided that the best choice would be the TCS 3200. We needed to determine how we were going to communicate the information being collected by our system, and in order to do this, we settled on the idea of delivering it through audio. But the question then arose whether or not we wanted to pursue Bluetooth or auxiliary connections in delivering this. When comparing Bluetooth versus auxiliary connections, we see that while the range of Bluetooth is far shorter, because of the fact that auxiliary connections can be as long as we want them, just based on the length of the wire, they do stand out because of their wireless functionality. And while their sound quality is a bit lower on average compared to wired devices, we decided to move forward with the Bluetooth because we wanted to reduce the amount of wiring surrounding the headset.
Next, we'll move on to the comparison and selection of software. We'll start with programming languages. I looked through and compared some of the more popular programming languages such as Python, C++, Java, C, and even assembly language. I ended up selecting Python due to its vast preset libraries that deal with image processing and color libraries like OpenCV. It's fast and easy to code, and although it's got limited hardware access and lacks real-time processing, its resources make it a very convenient and appropriate choice for our project. Next, moving on to IDEs, this was more of a preference selection. I researched a few IDEs like Visual Studio Code, Thonny, PyCharm, and Jupyter Notebook, which are all popular for Python development, and I landed on Visual Studio Code. It has an easy way to add in additional add-ons like OpenCD, and it's the IDE I am most comfortable working with. It has access to many extensions that will prove valuable in terms of hardware access, which is something that working with Python will definitely be a struggle.
The PCB design. The PCB design will consist of 3 distinct boards, and in the next few slides I'm going to talk more about them. Schematic. For the main PCB, in this first schematic shows the MCU, our ESP32 RAM32D, our CP2102 chip, our USB-A connection, 2 push-down buttons, our 3.3 volt regulator, and our connection for a 5 volt regulator. On the next schematic is just the connection pins for all our peripherals. So once for the servo motors, we added an extra one in case we were to decide to add an extra motor. On our system, we also have connections for the color emitter for the HCSR04 and connections to the Raspberry Pi. This is a PCB layout of our main board. So on one side is the ESP32, on the other side is the USB port. We also have the 3 volt regulator and our 5 volt regulator connection. The next schematic is our 5 volt regulator, the LM2596 step down regulator with a jack connection for our battery input and an LED to signal if the regulator is receiving voltage. PCB layout of our 5 volt regulator. On the bottom right corner is our output voltage for pin header. On the left bottom corner is the jack connection for our input voltage, and on the top left corner is the LM2596. TCS 3200 color detector PCB schematic. For this schematic, we just follow the online schematic found in circuitdigest.com. It has a 2 4-pin connection to the ESP32. PCB layout for the TCS 3200. For this, I follow the same component position as the one in the TCS 3200 board. I also use the same dimensions and sizes for the PCB board.
Next, we're going to look at software design. Firstly, here's the software flowchart. This first one is focused on the autofocusing system. Once the button is pressed, the edge detection algorithm is run repeatedly until either focus is achieved and audibly spoken, or if there is an issue, the program needs to run again. Similarly, on this next slide, we are focused on the color detection. It is started with a push of the button, and once the CMOS sensor takes a picture, the color analyzing algorithm is run repeatedly until it identifies a color that matches the results of the photodiode system, and then an auditory response is given, or the system receives an error and says try again. This next slide is focused on the use case diagram. This diagram is used to highlight how the system interacts with our internal and external parts. Our system has three main actors, which are the user, Raspberry Pi, and lens system. Everything inside the box represents the overall system, and it's basically the two different systems I just explained with the autofocusing and the color detection that I shown with the two flowcharts with the arrows showing the direct correlation. And lastly, on the next slide is the class diagram. This is used to show the structure of a program by breaking down the classes. We have 8 main classes. The main controller focuses on activating the autofocusing and color detection systems and then outputting the auditory response. The camera sensor and ultrasonic sensor classes just deal with gathering and outputting the data taken from these two devices. The edge detection and color detection algorithm classes also just deal with activating and running the two algorithms and outing the responses. And the motor control, color sensor system, and audio feedback are all response classes that make adjustments to the system based off the results of the two algorithms above.
Now let's explore our hardware testing.
For the testing of the ultrasonic sensor, since I utilized this in junior design, I just used the same code and same setup that we had there to test for the accuracy of the distance measurement. We used a MSP board and just a breadboard to power and connect the LED display. In terms of the ultrasonic sensor, it's not the most accurate form of measurement, but it should be good enough for what we need for our project. It works as accurately to about a couple of meters and as close to as about 1 millimeter.
Let's move on to the testing for the focusing system. The initial test was done as a proof of concept for the variable focal length. Using a negative 69mm focal length diverging lens and a positive 78mm focal length converging lens, we printed a frame that should have provided an optical power range between negative 1.5 diopters and positive 2.5 diopters. After testing, we observed that the range was closer to negative 0.5 diopters and positive 3.5 diopters. This demonstrated the functionality of a variable optical power, but there was a deviation of approximately positive 1 diopter between the calculations and the observations. For the next iteration of our focusing system, we utilized a negative 50mm focal length diverging lens and a positive 100mm focal length converging lens, which, according to our calculations, should have given us a variable optical power range between negative 10 diopters up to positive 10 diopters, more than enough to meet our needs. However, after testing, we observed that the actual power range was approximately negative 5 diopters up to positive 13 diopters. While there is still a deviation from the calculated value, this combination of lenses still surpasses our requirements. For our final design, we utilized the same lenses as the previous version. This time, however, we programmed in limitations on the maximum and minimum separation between the lenses. The maximum separation is set to 85mm, which corresponds to positive 3.5 diopters of optical power, with a focal length of 286mm. The minimum separation is set to 25mm, which corresponds to negative 2.5 diopters of optical power with a focal length of negative 400mm. In order to test the negative optical power, an additional positive lens with an optical power of positive 5 diopters was attached to the existing positive lens. With the separation set to 25mm, the total optical power of the system would then be positive 2.5 diopters with a focal length of 400mm. Upon testing, we successfully achieved our desired optical powers.
Now we'll go into our software testing. To test the camera module V2, we connected it to the Raspberry Pi via its camera port. Then we enabled the camera using that command shown there. Then we imported the Pi camera module and created several test images, one of which is shown there.
In terms of the edge detection, I just used a public GitHub code to see how someone implemented it and to see how the Raspberry Pi 4 would handle the image processing. In this example, this person implemented a Sobel filter to measure the contrast of the picture. This is meant to measure how much contrast is in an image and identify which sides of the pixels are the edges. It'll take in the top photo as input and output a 3x3 matrix with different colored squares. The darker the square, the more likely that part of the image is in focus. After some testing, I'll be able to determine an appropriate range of values to see if overall if the image is in focus or not for the autofocusing system. After initial testing, the Raspberry Pi had no issues running the program or producing a similar output.
We encountered difficulties, including latency between the input of commands to take photos and then receiving the photo itself from the CMOS code. However, we were able to optimize the loop statements to improve this latency. Our Raspberry Pi was additionally limited by needing to be plugged into a wall. However, we were able to circumvent this by acquiring a lightweight portable power supply that attaches to the arm. We also had several large and heavy components like the motors that restricted movement and reduced comfort. However, we were able to test smaller and lighter alternatives as well as acquire ball bearings that provided a suitable compromise. And finally, our initial focusing system lenses required large distances between the lenses, which resulted in a very large lens system that was extremely cumbersome. But we were able to test various alternatives until a more reliable and reasonably sized system was developed.
Budget. Our total budget is estimated to be approximately $474. The following table provides a detailed breakdown of the cost of all components required for our design. The majority of the budget is allocated to the MCU, PCB, and lenses. Work distribution. Our work distribution has been organized into 4 primary categories as outlined in the table. The development of the autofocusing feature, especially the adjustment of the lenses, is assigned to Genaro. Midhat is responsible for setting up the color detection system to ensure accurate results. Kayla is handling the software design, while I am assigned to the PCB design. However, we are collaborating closely to ensure the workload is distributed evenly.
Now for the progress and plan. The first week was utilized to regroup, discuss any component changes, and begin purchases of any remaining components. Weeks 2 to 3 were utilized to complete the PCB design and test components, as well as ordering any replacement components. Weeks 4 to 6 are where we are now. Aside from the critical design review, we are designing the housing as well as any structure that needs to be 3D printed. We'll also be assembling the autofocusing system. Weeks 6 to 9, we will be assembling the color identification system and combining the different systems to assemble the full prototype by the midterm demo. Weeks 11 through 12, we'll be finalizing the prototype and ensuring it runs smoothly. Week 13, we will have submitted the showcase video, and week 14, we will have our final demo as well as the senior design showcase. Finally, in week 15, the final report will be completed. Thank you for watching. Team P.A.U.L appreciates your attention.